and welcome to today's video where we're going to be talking through question 18, applications of method of moments as well as maximum likelihood estimators. Let's get started. You are given a random sample from a uniform distribution from 0 to theta, 1.3, 2.7, 8.2, 5.3, and x. You find that the estimate of theta using method of moments is equal to the estimate of theta using the maximum likelihood. Calculate the largest possible value of x. First off, for this problem, you need to know maximum likelihood estimation. So this is just a copy and paste from my walkthrough of question 15, but to briefly recap, you can look at the PDF, the probability of observing the data that you saw, under the assumption of whatever your hyperparameters were. So in question 15 it was alpha. Here we're going to be talking about theta. But you just look at the PDF for all the individual observations you have under the assumption of some hyperparameter, and the product of all of those is denoted with this capital pi. We then want to take the derivative and maximize, because these are independent samples, that's why they're all multiplied. We want to maximize the overall probability of seeing the data. So in application, the way you do that is take the natural log. It makes the derivative simpler, and you can do this because the natural log is a monotonic transformation function, so it won't change where the value is that produces the maximum value. So that's why we do that. So taking the natural log, taking the derivative of that, and because it's a natural log, we can convert this to summation, and that's why we do it. It simplifies the taking of the derivative, setting it equal to 0, and then saying, okay, what selection of our hyperparameters maximizes the likelihood of our data, and that's what maximum likelihood estimation is doing. The second method, and I try to look into why you would use method of moments, because to me maximum likelihood just seems better in all regards, and what popped up the most frequently that I saw was just that method of moments is computationally way simpler. Its application can, just be done much more simply, is the gist of it. And the way it works is you try to back into estimations of the hyperparameters using real simple moments. So a moment is just the expectation of e to the power of k. So the expectation of x, or expectation of x to the power of 1, is the first moment, and that's equivalent to just saying what's the sample, what's mu, and we estimate that using the sample average. And then the way you get an estimation of theta is you can look at your PDF. So using your PDF and invert it to back into, well, can I, instead of having this function that uses theta, say theta equals some function using the method of moments. And in this application we can do it using just the first moment, just looking at that sample average. So with those two bits of information, we can then jump into the actual calculations of the problem. So first off, considering the maximum likelihood, using a uniform distribution, the PDF is just 1 over theta. So the probability of any event is constant, and that's why it's a uniform distribution. And the area under the curve of a PDF has to sum to 1, so that's why it's 1 over theta. Next, what we could do, and this is me going into way more detail than I need to just because I'm trying to explain what's going on in this problem, but when actually doing the problem, you can kind of, maybe we'll recap and see some shortcuts we can take, because I didn't actually do this the very first time I was doing this problem. But if you want to formally go through taking the maximum likelihood estimator, we would take the derivative of the summation of the natural log of the PDFs and set it equal to 0, but we end up getting in a situation where we have to divide by 0, and that's no good. So just to visually show this, this is theta, and then this is the function that we're trying to maximize, the negative log of theta. And you can see that the smaller theta is, the further you're increasing the likelihood. So then we just need to take a step back and think about what are we actually considering? We're considering a uniform distribution. So if we know that the smaller the value, the better, it's going to increase the likelihood. We can then also say, well, if the maximum value we can see is 8, then the fact that we saw an 8.2 in our data is impossible. So really, the maximum likelihood estimator is the smallest value of theta you can pick that doesn't immediately invalidate the data you already have. So that's why the maximum likelihood estimator for a uniform distribution is just the maximum value that you saw within your sample. So translating that back to the problem, we saw 4 values and a fifth unknown, which is just x. So the maximum value we know of is 8.2, but if x is, let's say, 10, then our estimator would be 10. So our theta hat, our maximum likelihood estimator, is going to be 8.2 or x, dependent on the value of x. Next, going into method of moments, here we have our PDF. Again, it's just 1 over theta, but then what we can do is try to back it up and invert the expected value of x versus the theta. So the expected value of x is just the integral over the possible domain and just taking that probability weighted average. So it's x multiplied by its probability. You don't actually need to do this formal integration. I just wrote it out. If you wanted to, you could take this from the formula sheet. But taking the antiderivative, setting the range from 0 to theta, you end up getting that the expected value of x is just theta over 2. And again, this makes sense if you have a uniform distribution ranging from 0 to 10, you would expect that the average should be 5. So the expectation for x is just the maximum value divided by 2. What we can then do is invert this function. So we're going to say, well, I want to get a predictor for theta, so let's get theta alone, and that's just multiplying 2 by both sides. So our method of moments estimator is just going to be theta tilde equals 2 times x bar. And tilde is, I believe I remember from school that this is the common notation for method of moments. So if you see hat and tilde, the tilde refers to method of moments, and the hat will typically refer to the maximum likelihood estimator. So now that we have those 2 chunks completed, we can then try to bring it all together. And that is to say, for the problem, it wants to know what is that fifth unknown observation's value, what's the maximum possible value it could be, where theta tilde and theta hat are equivalent. So we know that theta tilde is just 2 times x bar, and theta hat is the maximum, so that's either 8.2 or x. So first off, just what is x bar? It's the summation of all the points divided by the sample size, and that works out to be 17.5 plus x over 5. Theta tilde is 2 times the average, so just multiplying by 2 and then simplifying, we get that it is 7 plus 0.4x. We then have 2 possibilities for our maximum likelihood estimator. It's either 8.2 if x is less than or equal to 8.2, or if x is greater than 8.2, we do this separately. And so we're just taking this estimator and setting it equal to either 8.2 or to x. Solving for both of these cases, we get that x is either 3 or 11.67. So these are the only 2 possible values that x can be where the 2 estimators are the same. And then we also are interested in which one of these is the largest, which is just 11.67. So scrolling back up to the problem, just to refresh, it says calculate the largest possible value that x can be. And since it's 11.67, that gets us the final solution of E. Thank you for watching today's video. If you found it helpful, please consider subscribing. Have a good one. Thanks.